So we've got a print in front of us. This is the mill 1 kit. I will point out the direction that we'll be milling, and then we'll talk a little bit about the matrix. In this case, I've got 10 points on the screen, 1 through 10. You see them scattered around. When we talk about what we're going to be doing with the mill program, I want you to understand the process that we're going to be using. The tool will basically wrap it over. It will point itself above. It will put itself above point 1. It will sort of drill down into the part 100 thousandths of depth. It will mill over to 2. It will pick up, wrap it over to 3, plunge down, mill over to 4, mill down to 5. It will pick up, wrap it over to 6, plunge down, mill up to 7. Notice this is an XY move, but the program has no problems doing that. It doesn't have to move in one axis at a time. It can move in both. After 7, it will pick up, wrap it down to 8, plunge down, mill over to 9, mill up to 10, pick up, and then go to home. And the home is also called the G28 position. And that is where the tool is out of the way and the part is up close to the operator or at the home position. Before I start programming, I really want to know where I'm going. The human mind doesn't like to do 2 things at once. It can, but it's not happy about it. So to get the most capacity of our brains on this problem, we usually like to do a matrix first. Matrix is a pretty straightforward thing. We're just going to map out the X and Y positions of all the points. In this case, you have, this is my origin. You can see it's called out right there in the origin. And I'm going to start off on point 1. So the first thing I'm going to do is get the measurements from here over to point 1. You'll see that it doesn't draw the dashed line all the way down, but unless it tells you explicitly that it is not true, you may assume that it is true that 1 and 10 are in the same X axis, that 7 and 10 are in the same Y axis, and that 3 and 8 are in the same X axis. Notice it does not tell you that 1, 2, 3, and 4 are all in line, but since it doesn't give you any other Y measurement on the right side, you may assume that they're all in line with the stack up of tolerances on the left. So here we go. You need to do this on your own with your calculator. I'm going to let the magic of Excel do this work for me. I'm going to do all the X's in a row and then all the Y's, and I'll tell you about why, no pun intended, that's the best choice later. So here we go, from origin up to point X. It's a given dimension, 0.375. From 1 to 2, it is 0.1 plus 1.250. For 1 and 5/8. Now notice I'm not doing any talk about motions or G codes or rapids or anything like that. I'm just getting my matrix written down. 0.3 is equal to 0.2 plus 1 inch. 0.4 is equal to 0.3 plus 1 inch. This is sort of an incremental mode. And if notice that it says 0.4 and 5, it does not say that they are not in line. We may assume that they are therefore in line. I screwed that up. There we go. I'm just going to write that one in 3.625 because again 4 and 5 are directly in line with each other. Now 0.6 is back further to the left. That should be a lesser X scale than 5, 4, 3 because you can see where that line drops down. I call this the sniff test. You just need to use some common sense in programming. This X should not be greater than 3, 4, or 5 because it's further back to the left towards the origin. So to do this, I'm just going to do my stack up. 0.375, 0.375 plus 750 plus 1.25. 375. That's to my that's to the X on 0.6. 0.7 X is 375 plus 750. 125, 1 1/8. All the way back to this X. Now I don't have to calculate this X. Notice that this dashed line tells me that X is in line with 0.3, therefore I just take that 0.3 to 0.625. I've stolen that X from 3 and I do the least amount of calculations possible. 0.9 is a given at 0.375 and 0.10 is the same, 0.375. Again, if it doesn't tell me that they're different, I may assume that they are the same. So those are all of my x's. Y is really straightforward. On the first one, I get to do the stack up of locations, 375, 1, and 750. And notice they don't tell me that these y's are different, therefore I may assume they're the same. All the way over to 5. 5 is the y for 4 minus 1 inch. Now we're going to the y for 6. Now the y for 6 is a stack up again. Here's from the origin up to these points. They don't tell me that these points are at a different y. I may assume they're the same, plus a ½ inch. So the y for point 6 is 0.375 plus 0.5. 875. 0.7 is the same setup as 0.375 plus 1. Point 8 is at a lower number. Again, use your common sense. It should be less than 6. In this case, it's a given. It's at 0.375. Is 0.8 less than 6? Yes, it is. By how much? A ½ inch right there. 0.9 is on the same level as 0.8, 0.375. And then 0.10, it's the same as 0.7, 1.375. Normally I would write that matrix out right in here so it's always there. I don't have to go back and find another sheet of paper. It's referenced right there on the print. You don't have to do it that way, but learn from hard experience and write them down on your prints as you go.